already. We could have, say, the limit as x approaches, let's do -5 from the right of 2x plus 1 over x plus 5 squared. Yeah, sure. All right, so for one like this, and we'll lose my balance here. Typically, right, with our limits, usually our first kind of thing we do is we just try plugging it in. If we plug it in here, -5. So, and I'm not plugging in a number that's close to -5. Right? I mean, we could, right? You plug in like negative, if I'm a little bigger than -5, I'm like -4 or -4.5 or -4.9 or -4.999. Right? Those are all numbers that are a little bit larger, meaning to the right of -5. But really, I just want to plug in actually -5. So if I plug in actually -5, I'm going to get 2 times -5, which is -10 plus 1, so -9 on top. And -5 plus 5 is 0. And 0 squared is still 0. So when we see that we have a when we see that we have a number over 0, I should really say a non-zero number over 0, we know it's going to equal some sort of infinity. Because what we've really got is we've got some number, that's not 0, divided by a very small number. And the thing we have to figure out is that really small number positive or negative? Well, in this case, since this quantity is being squared, it's definitely going to be positive, whether or not the insides are positive. For this particular one, the insides actually are positive, right? If you have a number that's slightly larger than -5 plus 5, it's going to end up being positive. Here's where you might want to think, okay, I do have something like -4.9. And -4.9 plus 5 is positive. And then the positive number squared is still positive. So I'm thinking I've got a negative number over a positive number. So this is going to end up being, well, a negative divided by a positive is negative, and it's infinitely large. If you want, because maybe you're like, well, why does dividing by 0 get us infinity? Well, because you really can't think of having a very, very small number. So just for example, let's say I plugged in -4.9999. So if I do that, the top is going to be almost -9. So I'm going to get approximately, I just heard a cat meow. I'm like, what's going on? No cats are stuck inside this room. They probably want to be inside this room. Sorry. So the top's going to be about -9. And the denominator is going to be, well, let's see, -4.9999 plus 5 is positive 0.0001 squared. The 0.0001 squared, that's 1/10, 100, 1/10,000. 1/10,000 squared is, let's just write it this way. 1 over 10,000 squared is going to be 10,000 times another 10,000. That's going to be pretty big, right? I've got 4 zeros there, I got 4 zeros there. That's going to be -9 times. I probably got the comma in the wrong place there. Yeah, I definitely did. Oh, well, sometimes that happens. It's really big, right? We don't even really care what the numbers look like. It's 900 million, sorry, -900 million. So you can see that when we get very, very close to the denominator being 0, the fraction is going to blow up, either to negative infinity or positive infinity. And then we can also look at the limit from the other side. The limit as x approaches -5 from the left of 2x plus 1 over x plus 5 squared. Same idea. We're just plugging in -5. The numerator is still going to be -9. The denominator, now the insides here, since we're a little bit less than -5, a number less than -5 plus 5 is negative. So we have a very small negative number, but it's getting squared. So we still have a negative over a positive, so the limit is -infinity. In this case, since the left-hand limit and the right-hand limit are the same, right? The left hand is -infinity, the right hand is -infinity. We can say that the overall two-sided limit is also equal to -infinity. It's kind of starting to go. It's time to start refilling. Let's see, can I use this red one? Sure, okay. I guess I can start using, I've got like a whole pile of orange ones over here. I don't like, the orange makes more of a mess. It kind of just seems to fly all over the place for some reason. Anyway, let's contrast that with this other one. Let's look at, yeah, I should think of something good here. One sec. Let me be clever for just a moment. Yeah, that's what I want. Right. Sorry, I have to think about this for just one sec so that it comes out to be nice. Yeah, let's do the limit as x approaches. Let me think for a second here. I want that. Right. Let's do the limit as x approaches. Sorry, I'm internally debating here. Yeah, let's do the limit as x approaches 1 from the right of x squared minus x cubed. Sure, that's fine. And then on the top we'll have, I don't know, 5x. All right, so same idea. We're going to plug in 1. We're going to get 5 over 0. Now the question is the denominator slightly positive or slightly negative? So I'm a little bit bigger than 1. Well, so here's where factoring would be a really good idea. So instead of actually doing this, I'm first going to rewrite it as limit is x. Oh, yeah, I did something. I'm going to make this a 5x plus 2 just so things don't just cancel out. So they'll make the top 7. Okay. So 5x plus 2 over, if I factor out x squared, now it's a little more obvious what's happening with the denominator. The top is going to be 7. The denominator is going to be 1 times 1 minus a number that is slightly bigger than 1, which is going to be slightly negative. So we get 1 times a slightly negative number. So here, positive divided by a negative. That's not a negative first power. That's just a negative superscript. Sorry, there should be no negative on there. That's going to be a positive divided by a negative. So this limit's going to be negative infinity. Whew. On the other side, if we take the limit, this x approaches 1 from the left of 5x plus 2 over x squared minus x cubed. This is where we have to be extra careful. If you try and go a little smaller than x, like x equal to 1, like if you try to pick 0 here, 0 minus 0 also makes the denominator undefined, or the denominator 0, which makes the whole thing undefined. So you can't pick something, like you could pick 1/2 and then try to figure out which one's bigger or smaller. Really though, again, it is almost always when you're trying to find the limit, it's usually in your interest to factor as much as possible. So if I factor out again the x squared, now I can more easily see that the numerator is going to 7. I'm just plopping that 1 in for x and getting 5 plus 2, which is 7. The denominator is going to be, again, 1 times a 0. But this time, since x is slightly smaller than 1, right, we're approaching 1 from the left, 1 minus a number smaller than 1 is going to be slightly positive. And then a positive divided by a positive is a positive number, and it's infinitely large because we're doing, right, again, dividing by 0 makes things get super large. And then the last thing I'll say about this one is that this means that the limit as x approaches 1, like the two-sided limit of this expression, since the right-hand limit and the left-hand limit are not the same, right? One's negative infinity, one's positive infinity. It means that this limit does not exist. You can write equals does not exist. I hate writing equals does not exist because it feels kind of weird, but yeah. So if the right-hand limit and the left-hand limit are the same, then the two-sided limit is also that thing. If the right-hand limit and the left-hand limit are different, then the two-sided limit doesn't exist. Okay. So hopefully that kind of helps with that. Let me grab one thing here. Yeah. Let's talk about continuity.
Can you briefly explain again?
Oh, sorry. Just one second. Let me turn up my volume here. Can you say that again?
Okay. Can you briefly explain again, back going to the problem that we just did, why that the limit of the x approaching 1 from the left, why it would be like the positive or the slightly positive 0?
Sure. So if I'm approaching 1 from the left, am I bigger than 1 or am I less than 1?
Less.
Right. So if I'm less than 1, is 1 minus a number less than 1 positive or negative?
Oh, I see. Okay, thank you.
Of course. Yeah, good question. And I will say, you're always welcome in a problem like that to kind of internally plug in a number. Like you could have plugged in something like 0.9, but usually, like, I don't actually want to plug that in here because it makes the math kind of hard. So I'm plugging in 1 for all the places where it's easy. And then here I'm like, okay, 0.9, 1 minus 0.9 is positive. So I'm getting a slightly positive number. Sure. So let's talk about continuity. And let's look at some pictures here. So here are some examples of things that are not continuous at a particular point. So here is a piecewise function, f of x equal to x squared when x is less than 2, and x plus 2 when x is greater than 2. Here's what it looks like. So it looks like your usual nice square function up until we get to 2. And this point here would be the 0.24. And then it looks like x plus 2 and x is bigger than 2, which looks like the line x plus 2, which kind of is this. So if that point were filled in, it would be continuous at 2, but it's not. So this function is not continuous at x equal to 2. And the reasoning I would give here is because f of 2 is undefined. Right? This function literally, right? They said skip 2. We're not going to define it there. We could, we'll come back to this one actually. Actually, sure. I'll try and make my life somewhat easy. So I'm going to define another function, which is going to be almost the same as this one. Let's make it a little bit different. I'm going to make this function g of x equal to the same function, except I'm going to also fill in for 2. So if x squared when x is less than 2, it is 6 when x is equal to 2, and it's x plus 2 when x is greater than 2. So it's the same graph, except at 2, we also get the point where y is equal to 6. So this function also discontinuous. And again, I imagine your teacher said something about this, but I'll say these words also. When we think about continuity just from a kind of very non-rigorous way, we're like, oh, can you draw the thing without lifting your pen off your paper or your pencil off your paper or your marker off the whiteboard? And clearly, right, I can't actually draw this without jumping over that point, whether there's a point there or not. So I cannot draw this without lifting my pen off the board, which indicates it's not continuous. What does the last, oh, sorry, some questions here. What does the last part of the g of x say? For x greater than 2, sorry, so it's the same as this. For it's equal to x plus 2 when x is greater than 2. And continuity versus just finding limits, what happens at x? That is an excellent point, Marshall. Yes, when we're talking about limits, we don't care what happens at the point we're finding the limit for. But for continuity, we really do care. In fact, and the definition of continuity, which we'll see in a moment here, definitely speaks to that. But here I would say exactly kind of what Marshall is pointing out, that f of 2 is equal to 6. But the limit, oh, sorry, not f of 2, g of 2, right? I called it g of x. Let me change the name here. G of 2 is certainly equal to 6, but the limit as x approaches 2 of g of x, well, as we're approaching 2, we see that the y values are approaching 4, whether we're approaching 2 from the left or 2 from the right. Right? At 2, the function is certainly equal to 6, but as we're getting close but not equal to 2, the y values are getting close but not equal to 4. that means the limit is 4. Again, I want to really, really stress, this doesn't mean g is equal to 4 when x is equal to 2. It just means that g, the y values are getting close to 4 as the x values are getting close to 2. That's what this says here. And we see that we have discontinuity. This is called a point discontinuity or removable discontinuity. Not that that super matters, but that's kind of going on here. So you can have something being discontinuous because the function is not even defined there. You can have something being discontinuous because the function exists and the limit exists, but they're not actually the same. And then there's even, and I kind of skipped over one, but let's go back for a second. You could also have something like this. Let me do this piecewise function. F of x equal to something also, again, similar. Let's make it x squared when x is less than 2. And let's make it x plus 3 when x is greater than or equal to 2. My cat is losing her mind out there. I don't know what is going on. I'm gonna let her see. Sorry. Just one sec. Can I help you? Okay, you can hang out in here. I know you're gonna want to leave though. Sorry, she's I can show you the cat. She does not want to be picked up right this moment though. She's just, I don't know. Okay, if I have a chance, you guys will definitely see my cat sometime this quarter. But right now might not be the right moment. Did you want to sit in my chair? Is that what you want? Okay, anyway, sorry, back to the math. So this one looks like this. And right, it's open there because it's equal to x squared when x is less than, but not equal to 2. So we have that there. And then when x is equal to 2, 2 plus 3 is 5. So this line, y equals x plus 3, starts here and then goes off to the right like that. So here, clearly, again, just visually looks discontinuous, right? We have a jump there. And I would say, right, here it's pretty clear that the limit as x approaches 2 of f of x does not exist because the left-hand limit and the right-hand limit are different. The limit as x approaches 2 from the left, well, as x approaches 2 from the left, the y values get closer and closer to 4. As x approaches 2 from the right, the y values get closer and closer and closer to 5. So the limit doesn't exist. How do we solve this algebraically? By solving it, do you mean evaluating the limit, Lauren?
Like, for example, I'm just looking at my notes from Nguyen's class. So basically, she would ask a question like, is f continuous at x is equal to 2 for f of x, and then give like the domain restrictions and stuff. So how would we go about solving that algebraically?
Sure. So if you were just given this function and not the graph, the way I would show that this function was discontinuous at 2 is by doing this, but I would do a little more work, meaning I would say, okay, well, the limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the left of, well, I'm approaching 2 from the left. That means x is less than 2. That means I have to use this piece of the function. And then I'm going to evaluate the limit like we usually evaluate limits, meaning I'm just going to try plugging it in, which is totally valid. So if I plug in the 2, I get 2 squared, which is 4. For the right-hand side, same deal. When the limit as x approaches 2 from the right, which means I'm bigger than 2. So then I get the limit as x approaches 2 from the right of, well, if I'm bigger than 2, I have to use this piece of the piecewise function. And then I'm going to evaluate the limit by whatever means necessary. In this case, I can just plug it in again, and 2 plus 3 is going to give me 5. And then since this limit is not equal to that limit, the limit doesn't exist. And that we'll see in just a second here. Saying the limit doesn't exist at a point is a sufficient condition to say that the limit or that the function is not continuous there. Okay. So that's how we can show a function is discontinuous. That's one of the ways we can show a function is discontinuous at a point, is by showing that the limit doesn't exist there. And so let me see here. So we've kind of seen the three ways a function can be discontinuous at a point. The limit cannot exist. A function cannot exist at that point, or the function and the limit can both exist but not be the same. Which kind of leads us to the definition, which is that the limit and the function both have to exist and be the same for the function to be continuous at a point. I also want to point out that so if you were talking about this function, or this one or the previous one, you would say it's a discontinuous function. But what we really mean with that language is that it's discontinuous at least in one spot. This function is continuous almost everywhere, right? It's continuous literally at every point except for 2. I would still call it a discontinuous function because it happens to be discontinuous at 2. Same deal here. Right? This function is continuous everywhere except for 2. We would still refer to it as being a discontinuous function. So discontinuous just means it's discontinuous at least at one spot. And when we say something is continuous, what we frequently mean is that it is continuous everywhere. So, definition of continuity. F of x is continuous at the point, we usually say x equal to c. You can pick kind of any letter you want. If and only if. By the way, you might see people abbreviate if and only if with an if with 2 f's. All that means is that it's true either way, meaning if it's continuous, then these things are true. And if these things are true, then it's continuous. So we usually write this as 3 things, even though the third one is the only one that really matters. And I'll say more about that in a second. So the first thing we need is we need that f of c has to exist. We need the limit has to exist. And then finally, we need them to be equal to each other. Now, I will point out that you really only need to say the last one, because for the last one to be true, the first 2 have to be true. Like the only way that the limit is equal to the function is if they both exist and are the same number. They can't both not exist and be equal. You can't say, oh, this one doesn't exist and this one doesn't exist, so they're the same thing. They just don't exist. So that is something to be aware of, that you will often see in textbooks. Then just write the definition of continuity is this last part, but it's usually easier to kind of conceptualize if we think of it as a 3-step process. Where first we check this, then we check this, then we check this. So this is our definition of continuity. And so if someone asks you to show something is continuous or discontinuous at a particular point, they're going to expect you to go through these steps and ask yourself, does the function exist there? Does the limit exist there? And does the limit equal the function? If you can say yes to all 3 of those things, then it's continuous. If you end up saying no to any of these things, it is not continuous at that point. Sorry, I'm getting hiccups. One sec here. Okay. So let's look at a couple examples, and then we'll finally we'll roll around to the question Marshall asked me, which is definitely a good question. Yeah, cool. Am I looking at the right thing? Oh yeah, okay, sure. Yeah, let's do this. So I would definitely ask a question like this on a test. So typically we ask where something is continuous, but the way we answer the question is by finding where it's not continuous. So I would ask, where is this function continuous? But then our job is going to be to find where it's not continuous and say everywhere except the places where it's not continuous. So here's the function. It's a piecewise function. Most of the time when we're asking questions about continuity, we're usually using piecewise functions because they're the ones that are most easily made to be discontinuous somewhere. So let's look at f of x equal to 6 over x plus 2 when plus e to the 5x when x is less than 0. 4 cosine of pi x when x is between 0 and 1. So x is greater than or equal to 0, less than or equal to 1. And the third piece is going to be x to the 17th power plus the cube root of x plus 6 when x is greater than 1. Okay, so there's my piecewise function. So here's the thing to be aware of. I mean, there's a lot of things. Piecewise functions are always potentially discontinuous when you change from one piece to the next. So certainly we need to consider what's happening at 0 and what's happening at 1. Those are places where it may be discontinuous. There is actually one other place where this function is definitely discontinuous. Does anyone see where this first piece might have a discontinuity? The first one. So this is 6 over x plus 2 plus e to the 5x. I'm not saying like between here and here and here and here. I'm saying this function, this piece of the function all by itself, there is a place where it might be discontinuous. Specifically where you might be trying to divide by 0. Oh yeah. Right, if x is equal to what? What's going to make us divide by 0 here? X is certainly discontinuous at x equal to -2. Right. Because if you plug in -2, you get 6 over 0 undefined. And so I should point out. So I'm going to change this just slightly and then we'll come back. So what if instead this said 6 over x minus 2? Well, we might think for a second that this function was discontinuous at 2, but the issue is that we're not actually, the function isn't equal to this when x is equal to 2, right? The function's only equal to this when x is less than 0. So if it was written this way, we wouldn't have a discontinuity for 2 at x equals 2, because 2 isn't where this piece is being what the function is defined to be. But since it's x plus 2 and -2 is in this domain here, then it's definitely discontinuous there. All right, so you guys wrote some chat. Okay, cool, yeah. I didn't see what number 28 was, but I can definitely take a quick look if I can remember where I put things. Maybe, yeah, there we go. Oh yeah, we're definitely going to get to one like 28 for sure. That's what we're going with. We're going to 20%. So yeah, so this says, let me read it to you. This is 6 over x plus 2 plus e to the 5x when x is less than 0. This is 4 cosine of pi times x when x is between 0 and 1. And this is x to the 17th plus the cube root of x plus 6 when x is greater than 1. So we definitely see discontinuous at -2. Let's talk about at x equal to 0. Because we always have to consider the places where we change from one piece to the next piece. So at x equals 0, we're going to check the 3 things. Thing 1, what's f of 0? Does f of 0 even exist? It exists. F of -2 doesn't exist, right? It's undefined. It's division by 0. But f of 0, I'm going to look at the piece where x is equal to 0, which is this middle piece here. I'm going to plug in 0. I'm going to get 4 times cosine of pi times 0. Pi times 0 is 0. Cosine of 0 is 1. So I get 4 times 1, which is 4. Okay, now I'm going to look to see if the limit exists. Typically, almost always, I should turn on my light. It's a little dark in here. Unless you guys think it looks terrible. So for piecewise functions, if we're trying to find the limit as x approaches 0, we're almost always going to have to approach the 0 from both sides. So I'm going to do the limit as x approaches 0 from the left of f of x, and the limit as x approaches 0 from the right of f of x. And they're going to end up using different pieces. If we're approaching 0 from the left, that means that we are less than 0. For less than 0, we have to use this piece right here. So it's going to be 6 over x plus 2 plus e to the 5x. The nice thing is that usually, not always, but usually, these are almost always going to be some things where we can easily evaluate the limit just by plugging in. If I plug in 0, I get 6 over 2. That's well defined. And I get e to the 0. also well defined. So I get 6 over 0 plus 2 plus e to the 5 times 0. That's going to be 6 over 2, which is 3, plus e to the 0, which is 1, which is 4. Typically, one of the pieces you've already kind of done when you found out what it was equal to in 0. So when I do the limit as x approaches 0 from the right, it's the limit as x approaches 0 from the right of, well, if I'm to the right of 0, it's not this piece, even though x is bigger than 0 here. It's going to be the piece that's bigger than 0, but also close to 0. So right here, x is just bigger than 0. So I'm going to use that piece of the function, which is 4 cosine of pi x. But we already know that when you plug in 0 for x here, like we did when we showed what f of 0 was, we're going to get 4 times cosine of 0, which is going to be 4 times 1, which is going to be 4. And now, since the left-hand limit and the right-hand limit are the same, we can say that the limit does exist. So the limit as x approaches 0 of f of x is equal to 4. Be careful. I've definitely seen people get to this step and say, oh, it's continuous because the limit exists. We have to say one more thing. We have to say that, oh, the limit exists and it is equal to the function value. So I'm kind of run out of room here. Step 3, we can definitely see that the limit as x approaches 0 of f of x. Oh gosh, come on, James, you can write that better than that. The limit as x approaches 0 of f of x is equal to f of 0. So f of x is continuous at x equal to 0. And then we would do the same process again for x equal to 1, which I don't have enough room to do on this side, so we're going to have to go to the other side of the board. That's all right. So for x equal to 1, here's what we're going to do. We're going to plug in 1, and we're going to end up plugging it into this function again. And then we're going to do the limit as x approaches 1 from the left using this piece. The limit as x approaches 1 from the right using this piece. Okay. I suppose I can write the function again here. All right, here's our function again. 6 over x plus 2 plus e to the 5x for x less than 0. It is 4 cosine of pi x for x between 0 and 1. And it is wacky thing on the other side, x to the 17 plus cube root of x plus 6. When x is larger than 1. So let's find f of 1. So f of 1 is going to be 4 cosine of pi. Cosine of pi is negative 1, so 4 times negative 1 is going to be negative 4. All right, let's look at the limit. So the limit as x approaches 1 from the left. The limit as x approaches 1 from the right. I'm approaching 1 from the left. I'm using this piece of the function because that's where I'm just less than 1. So 4 cosine of pi x. And it's going to be the same as that, right? Because it's literally just plugging in 1, getting 4 times cosine of pi, which is negative 4. Typically in these sorts of problems, after you've evaluated the function at 1 in this case, right, x equals 1, one of the one-sided limits is going to have the same value because you're using the same piece of the piecewise function. For the other side, when x is approaching 1 from the right, we're using this. And we're going to get x to the 17th plus the cube root of x plus 6. I do think you should write out the function before you jam 1 into it. Plugging in 1, we're going to get 1 to any power is 1. So 1 plus 6 is going to be 8. Not the same. So at this point, we can stop and say, oh, f of x is not continuous at x equal to 1. Often teachers like it when you write the reason why it's not continuous. So it can either not be continuous because f of 1 doesn't exist. Oh, it did exist, so it's definitely not because of that. Or because the limit doesn't exist, which is the case here. Or because the limit doesn't equal the function. But in this case, it is specifically because the limit does not exist. So it's not continuous at x equals 1 because the limit as x approaches 1 of f of x does not exist. Okay. Finally, to answer the question that we started with, which is where is this function continuous? Well, we know it's not continuous at 1, and it's also not continuous at -2. So it's continuous everywhere except for that. So we don't want -2, we don't want +1, but we want literally every other number. So we would say it's continuous on the interval from -∞ to -2. In fact, let me write it down here. Union -2 to 1, union 1 to infinity. That would be the interval or domain of continuity. Why not -2? Because, right, we said that if you plug in -2, you're going to get division by 0. And that means it's undefined. That's why not -2. My cat keeps opening my door. Okay, here she is. She's a big cat. She's a black cat. Look into the camera. Can't really see her eyes because there she is. Well, yeah. Her name is Lily. We have another cat named Sparky who likes to hang out behind my computer because I have a time machine back there that is very warm. She likes to be warm. Yeah, this one's definitely our louder cat. The other one is not very loud usually. All right, so let's do. Thank you. Yes, they're both old cats. They're like 16, 17 years old. They're getting up there. Been around for a while. All right, so let me go ahead and do a question similar to problem 28 from your exam review. I think I have one here. Yeah, that's not what I want. We'll do that. Sorry, it's hard to show. Sweet, look at this. Let me make sure it's not exact. I mean, I guess it's not. So here's what I've got. Yeah, find A and B so that the following function, f of x equal to, I see someone's written something, but just let me write this down first, equal to ax plus 1 when x is less than 2, ax squared plus b when x is between 2 and 3. Sorry, I'm a little messy there right now. Yeah. And then finally, -5b when x is greater than 3. So we want to find a and b so that this is continuous. Continuous, and when I say it is continuous, I mean it is continuous everywhere. And I should point out, oh, sorry, let me read what. First time we verify the function is 1 to 1. Yeah, sure. We can talk about 1 to 1. So, time is it? Yeah, okay. So what I want to say here is that you should be aware that ax plus 1, ax squared plus b, and -5b, those are all continuous everywhere they're defined, right? They're all polynomials, and polynomials are continuous everywhere. In fact, before we do this, I just want to kind of go back to the other side for 1 second and write down something that I know I saw. So just so you guys know, most functions we deal with are continuous most places. Polynomials, as well as sine of x and cosine of x, and e to the x, and 2 to the x, or any non-zero number to the x. These are continuous everywhere. It's kind of useful. So polynomial, like positive integer powers of x, right? Like, 5x to the 6 plus 2x squared plus 1. And then there's some other functions that are continuous almost everywhere. Rational functions, meaning things like x cubed plus 8 over x squared minus 7x. Sorry, I'm trying to make up something that's not dumb. Plus 10. Rational functions, the rest of the trig functions, secant, tangent, cotangent, and cosecant. What else comes to mind? A natural log or any logarithmic function. Natural log of x, log base b of x. These functions are continuous on their domains, meaning they're continuous where they are defined. Now, all these functions can be undefined where their denominator is 0, right? This function has a denominator. It's definitely undefined at x equals 5 and x equals 2. Secant, tangent, cotangent, cosecant all are trig functions that have denominators. Secant is 1 over cosine, tangent is sine over cosine, cotangent is 1 over, or sorry, cosine over sine, and cosecant is 1 over sine. All of these are definitely continuous where they're defined, but they're not defined at various places, like pi or pi over 2. And then finally, natural log and log. These are the only ones where you have undefinedness, where it's not division by 0, but we know the natural log function looks like this. It's definitely continuous on the interval from 0 to infinity, but then undefined for everywhere else. So continuous on its domain, continuous where it's defined. So most of the functions we deal with that aren't these weird piecewise things on the other side, most of the functions we deal with are continuous wherever they are defined, which is nice. So back to this mess. The way we solve a thing like this, and so here's what we need to be true. We need the functions to exist at every point. They do. We also need the limits to exist. And the limits existing is where we're really going to be able to solve what A and B should be. So we need the limit as x approaches 2 of f of x to exist. Meaning we need the limit as x approaches 2 from the left, which is going to use this piece. We need that to equal the limit as x approaches 2 from the right, which is going to use this piece. What this is going to end up doing for us is going to end up meaning that we're going to plug in the 2 for x, right? How do we evaluate these limits? We just substitute in what x is approaching for x. This is going to be a times 2, or 2a, plus 1. And this is going to be, let's see, I'm plugging in 2 for x, and we get 4 times a plus b. Now, that's not enough to figure out what a and b are, but it's a first step. We also need the limit as x approaches 3 to exist. Now, a lot of people kind of skip the limit writing step and just plug in the numbers. I don't know how your teacher feels about that. I think it's worth writing out the limits, but you might not. So I need the limit as x approaches 3 from the left of f of x, which is going to be the limit as x approaches 3 from the left. So again, if we're left of 3, we are less than 3, right? Left and less, we'll start with L. That's really what I think about. Oh, if I'm left, I'm less. If I'm less, I'm left. So if x approaches 3 from the left, we're using this piece. If x approaches 3 from the right, there's no nice word that starts with the right to mean greater than, as far as I can think of. If x approaches 3 from the right, we are bigger than 3, so we're using this piece here. So if I plug in 3 for x, I'm going to get a times 3 squared, which is going to be 9a plus b. If I plug in 3 for x here, oh, there's no x to plug in for, so I just get negative 5b. Well, then we can try and isolate one of these variables here. So let's see if how do I want to do this? I don't know. There's lots of ways you can do it. I guess I will. Well, let's see. I've got a single b here. That's probably going to be the easiest to solve for. So let's do that. So here, b is equal to, subtract 4a. I'm going to have 2a minus 4a is negative 2a plus 1. And then I'm going to substitute that in for b over here. I suppose before I do that, I bring the b over here. So I'm going to have 9a equal to negative 5b minus b is negative 6b. And then I guess I'm going to go up here. I'm going to plug in what b is equal to for b here. So I'm going to have 9a on the left equal to negative 6 times b, which is negative 2a plus 1. And then we're going to solve for a. So let's see. Sorry, I know things are getting very squeezed in here. So let's see, negative 6 times negative 2a is 12a, and negative 6 times 1 is minus 6. Subtract 12a, 9a minus 12a is negative 3a, equal to negative 6. So a is going to equal negative 6 divided by 3, which is positive 2. And then we can go back and see that b is equal to negative 2a plus 1. So b is going to equal negative 2 times 2 plus 1, which is going to be negative 3. So that's typically how these problems end up working out. You set the limits equal to each other, you get an equation involving a and b, then you do it again for the other place, you get an equation involving a and b, and then you've got two equations with two unknowns, and you can solve for a and b. Are there questions about this one? Okay, so, I mean, you can certainly do more practice with continuity, right? You can definitely, it's good to kind of remember the definition, right? The function has to exist, the limit has to exist, and third, and most importantly, they have to equal each other. Maybe not most importantly, but certainly important. But let us go ahead and kind of shift gears. Yeah. Yeah, I'm not sure if we'll get to the one-to-one thing or not. I will try. Let's start talking about the limit definition of the derivative. Because even if you haven't started talking about it yet in your class, I think everyone has, but even if you haven't, you're certainly going to. And the limit definition of the derivative is explicitly related to the difference quotient. Yeah, I should do some explaining here. So the idea with the limit definition of the derivative is that, for lack of a better term, we're trying to find, some people want to say it's the slope of the tangent line at a particular point. You could also think about it as just the rate of change of the function. So let me draw a picture. So yeah, here's some function. And I'm really interested in knowing what the rate of change of the function is, meaning how is y changing as x is changing? Well, that's just another word for slope, right? How is y changing as x is changing? We're talking about the change in y compared to the change of x, or the change in y divided by the change of x, which I think we know is what slope is, right? Slope is change in y over change in x. But this is also a rate of change, right? How y is changing as x is changing. So we want to know right here, how is y changing as x is changing? Well, we're really asking, what's the slope at that point? Well, the way we're going to do this, or the way we're going to kind of imagine it, is we're going to say, well, I don't know how to find the slope between just one point. So we're going to have a second point over here. And say, well, if I call this point x, I'm going to call this f of x. So that's point x comma f of x. And I personally like to use an h. Some people like to use a delta x. Either way is fine. I'm going to call this point x plus h. Your teacher might have called it x plus delta x. Either way is fine. So what I'm saying is this amount here is h, or you might be saying this amount here is delta x. Either way. H is just easier to write. So what I'm going to do is I'm going to say, well, I know how to find the slope of the line between 2 points, right? We are very good at that. So the slope of that line is the differences in the y's. And so I can actually write down what this point is, right? This point here is x plus h comma f of x plus h. And this point here is x comma f of x. So the slope between these 2 points is the difference quotient. It is the differences in the y's, f of x plus h minus f of x, divided by the difference in the x's, which is x plus h minus x. The denominator simplifies to just h. So we get f of x plus h minus f of x all over h. And now here's the idea that kind of brings it all together. If we're going to find what the slope of the tangent line is, what we're going to do is we're going to let this point move towards that other point. So what we're actually going to do is we're going to say, well, what if I moved this point a little bit closer to now be here? And then I drew, and so my pictures are going to get messy here. What if I drew this? Oh, by the way, the line through 2 points is called a secant line, and the line through 1 point is called a tangent line. So this secant line, which I know is not drawn very well, the slope got a little bit closer to the slope of the tangent line. And then what if I let my point get a little bit closer? Well, that secant line is going to have a slope that's even closer to the tangent line slope. So the idea here is that if we let this point get closer and closer and closer to the point we're trying to find the slope of the tangent line at, the slope of the secant line approaches the value of the slope of the tangent line. So what we can say here is that the slope of the tangent line, all right, is m sub tangent, is equal to the limit of the slope of the secant line. Well, the limit is what? Well, the limit as x plus h gets closer and closer to x. Well, if x plus h is getting closer and closer to x, it means that the value of h is getting smaller and smaller and smaller. So there's your limit definition of the derivative. And notably, it's just the limit as h goes to 0 of the difference quotient, which we already saw before. Not the limit part, but the difference quotient part, right? We've definitely seen this. So let's do some examples, which will definitely involve simplifying the difference quotient. And so this is why we practiced, this is why at some point in your mathematical career, someone should have had you practice simplifying something like this, because our goal is to be able to plug in h equal to 0. But to be able to plug in h equal to 0, we really need to not have an h in the denominator. So our driving force goal here is to cancel that h out, is what we really want to happen. So that then we can substitute h equal to 0 for the rest of the h's. Let's look at some examples. And this should address the question of simplifying the difference quotient, as well as learning about the limit definition. So let me actually look at one thing here, just so I can kind of be on point with this. Yeah, all right, sure. Okay, so let's say that our function is negative 6x squared plus, sure, 5x. And I want to find the limit definition of the derivative. So I want to, and we typically write this with this notation, f prime of x, although there's literally like 4 or 5 or 6 ways you can write a derivative. You can write it as f prime of x, you can write it as df dx, you can write it as f subscript x. This is kind of pretty standard, but really any of these is fine. So f prime of x is equal to the limit, h goes to 0, of f of x plus h minus f of x all over h. And I have found over the years that at least at first, it's probably worthwhile to actually write out these things kind of on their own. We already have f of x. But let's write f of x plus h just to make sure that we get it right. So f of x plus h, we are taking our f of x, and everywhere we have an x, we're subbing in an x plus h. So this is, instead of negative 6x squared, it's negative 6 times something squared plus 5 times something, right? One student told me what they do, and I've kind of taken this to heart, is they replace every x with a parentheses, and then whatever's inside the parentheses here goes inside the parentheses there. That was just the way that made it easiest for them, which I think is not a bad idea. So there we go. I've got negative 6 times x plus h squared plus 5 times x plus h. And then I'm going to write all of that in this limit here. So it's going to be the limit of all of this minus all of this divided by h. And you should write the divided by h every time. I've definitely seen people over the years kind of not write the divided by h until the very end, which is fine. It's not fine really because it's not technically the same. So, but it's not that bad. All right, anyway, sorry. Less talking, more doing. So negative 6 times x plus h squared plus 5 times x plus h minus all of negative 6x squared plus 5x divided by h. Okay, our goal is to cancel out this h. Our intermediate goal, before we get to that last goal, is to cancel out all the things that don't have an h in the numerator, which is going to mean we're going to have to simplify this. This is where our algebraic methods of solving limits are going to come into play, where we're either going to factor and cancel, or we're going to multiply by a conjugate, or we're going to use a common denominator. Those three things come up a lot in these limit definition questions. Here, we're going to multiply it out and then do some factoring and canceling. So x plus h squared is x squared plus 2xh plus h squared. Distribute the 5, so I get plus 5x plus 5h. And then we always need to make sure that this minus sign gets distributed to whatever's in there. So it's going to be a minus, so plus 6x squared and a minus 5x divided by h. Now we can't cancel the 6x squareds yet, but we can certainly cancel the 5x and the negative 5x. Before I can cancel the 6x squared, I have to distribute this minus 6. So I'm going to get the limit as h goes to 0 of negative 6x squared and minus 12x minus 6h squared. Right? Distribute the minus 6 to each of those terms. And then I've still got the plus 5h, the plus 6x squared, all divided by h. And now the negative 6x squared and the positive 6x squared should cancel out. And now we've achieved our intermediate goal. All of the, oops, we have not. Well, we have, I just made a mistake, a small mistake. Here I had negative 6 times 2xh. So I should have had negative 12 times xh. I forgot the h there. Sorry about that. Now we've achieved our intermediate goal, which was to cancel out all the non-h terms in the numerator. Right? I'm left with a negative 12xh minus 6h squared plus 5h. Everything left has an h in it. At this point, I like to take the additional step of factoring out an h from the top, but some people just like to cancel one h from each of the terms in the numerator. I'm going to factor it out, but either way is okay. So I'm going to write the limit as h goes to 0. I'm going to divide out an h from each of the terms in the top. So I'm left with an h times that negative 12x, a minus 6h, and a plus 5 divided by h. Those h's cancel. My h divided by h is 1. And then we can write it as, sure, I can write the limit as h goes to 0 of negative 12x minus 6h plus 5. The remaining h's get replaced with 0. So I get negative 12x minus 0 plus 5, which is just negative 12x plus 5. And that's our answer. That is the derivative of this function, or it's the slope of the tangent line at any point x. So I could then ask you a follow-up question like, what is the, and let me see how they phrase this here. Sure. What's the slope of the line tangent to f of x at the point x equal to 2, for example. And the nice, easy way of doing this is to have already done this work and then just plug in x equals 2. So we can say, oh, f prime of 2, if I plug in 2 for x, I get negative 12 times 2, which is negative 24, plus 5, which is negative 19. So the slope at that point would be a slope of negative 19. Does that make sense? Yeah. Right. If you were to graph this, negative 6x squared plus 5x, I'm going to graph it for you guys not very well. It's opening downwards. So if I was going to graph y equals to negative 6x squared plus 5x, I'm going to graph it, not doing too much work. If I factor out x, negative 6x plus 5. So I have x equal to 0 as an intercept and x equal to 5/6 as an intercept. Sure. So it looks something like this. And way over here at 2, right? If I go way down here, the slope of the tangent line is super steep and negative. So negative 19 seems like a reasonable answer for the slope of the tangent line at that point. Yeah, I could also ask for the slope of the tangent line at x equal to 1. F prime of 1, if I look back at my derivative, negative 12x plus 5, f prime of 1 is negative 12 times 1 plus 5, which is negative 7, which again seems reasonable because we're just like right here and it's a pretty steep negative slope. Okay. Let's look at another example. We're definitely going to do more with this next week. But yeah, I'm going to erase this. So what if I wanted to find f prime of x for f of x equal to, how complicated do I want to make this? Not that complicated. Square root of 2x plus 1. So again, when someone says find the derivative, find f prime of x, and I should be more specific, find f prime of x using the limit definition. Right? They will say that. If they don't say these words in the future, you should assume that we do not have to use a limit definition. You should only use the limit definition if you're being asked to, really, because we're going to learn other ways to find derivatives that are going to make life much easier. But for now, we've got the limit definition. So we're going to do the limit as h goes to 0. I like to actually write it out, meaning f of x plus h minus f of x all over h. So this is going to be the limit as h goes to 0 of, so f of x plus h, right? I'm taking my function, and wherever I have an x, I'm plugging in x plus h. So it's going to be the square root of 2 times parentheses plus 1 minus f of x, the square root of 2x plus 1. So there's your f of x, there's your f of x plus h. Something to be aware of as well, the h has to go right with the x, right? You definitely don't want to write like, so this is not the way to do it. It's not the limit as h goes to 0 of the square root of 2x plus 1 plus h minus the square root of 2x plus 1 all over h, right? This is not correct, because if you do this, you're going to get those canceling, and then h divided by h is just 1. If your derivative is 1, always, right? This doesn't care what x is, the derivative is 1. If your derivative is 1, that means your slope of your tangent line is 1, which means your original function was just x, or x plus a number. So here's what I want to impart to you. If you got your derivative to equal 1, unless you started off with your function being f of x equal to x plus a number, it means you probably made an error. So typically, if you're getting 1 as your answer, you should probably go back and double check. Okay, but we're not getting 1. So what do we do when we have a square root minus a square root? What's our plan of attack? First of all, I'm going to write this as 2x plus 2h just to make my life slightly simpler. And what do we like to multiply by when we're stuck with square roots? Yeah, the conjugate, Gabriella, exactly. So I'm going to multiply by the square root of 2x plus 2h plus 1 plus the square root of 2x plus 1 over the same thing. Of course, I'm going to run out of room. Sorry, I wrote 2x plus 2h plus 1 plus the square root of 2x plus 1. And then, so here's two things. Thing one, I definitely don't want to multiply at the bottom because one, they're not conjugates, but even more importantly, I know I want to cancel this h out. If you know you want something to cancel out, you always kind of want to leave it separate from the rest of the stuff. So we know we're going to write the denominator as just h times that stuff over there. Square root of 2x plus 2h plus 1 plus the square root of 2x plus 1. The numerator, or the things that are conjugates, we always want to multiply out. And it's always going to be the first thing squared. So the square root of 2x plus 2h plus 1 squared is just 2x plus 2h plus 1 minus the second thing squared, which is 2x plus 1. Now, if we're not careful like this, we're not going to get what we want. We know we want all the things that don't have h's in the numerator to cancel out. But looking at this, if I've made a mistake here, which I'm going to correct in a minute, but here it looks like I have 2x minus 2x. Okay, those cancel. But it looks like I have a plus 1 plus 1. And those don't cancel if I forget that I have to have minus all of that. Exactly. I need parentheses there. So here's what I would always say. If you see that things aren't canceling the way you expect them to, go back and check and make sure you've got parentheses or you've distributed the minus sign appropriately. Things should cancel. But don't just cancel them because you like, the other thing I want to say is, if you forget the parentheses and just say these cancel, someone's going to have a problem with that. So don't say things cancel unless they actually cancel. We know that they're supposed to cancel, so make sure that you have the necessary parentheses or distribution or whatever. So, yeah. All right, we're getting a little messy here. So the 2x minus 2x will cancel. The 1 minus 1 will cancel. So we're going to get the limit as h goes to 0 of 2h on top over h times all that stuff on the bottom. 2x plus 2h plus 1 plus the square root of 2x plus 1. Okay. H divided by h is 1. So I'm left with 2 over all this, and then the rest of the h's go to 0. Do I have room to write this down somewhere? Sure, I can write it up here. I know it's never ideal. So I'm just going to let the rest of the h's go to 0. So this limit's going to equal. So I'm plugging in 0 for h, so I don't write the limit anymore. Whenever you're plugging in what h or x or whatever is approaching, you no longer write the limit. So I'm getting 2 over the square root of 2x plus 0 plus 1 plus the square root of 2x plus 1. Those are the same. Something plus itself is 2 times that thing. So I've got 2 over 2 times the square root of 2x plus 1. And then the 2's cancel there, and you get 1 over the square root of 2x plus 1. Be careful, right? You are adding those square roots together, you're not multiplying them. If you multiply them, it would just be 2x plus 1. But since we're adding, it's 2 times the square root of 2x plus 1. And the 2's cancel. All right. There was one other example I wanted to give you guys just because I saw it in the homework and it looked easy to do, but also worth mentioning. And then I think I can get to the question of one-to-oneness. So two interesting functions. What if I had f of x equal to 6x? So here's the thing, 6x, you all know the slope of that line. What is the slope of that line? Nobody wants to write anything. It's okay. The slope is 6. And so here's the thing about straight lines. Right? Here's my line 6x, because I know it would be steeper than that, whatever. If I look at this point here, the tangent line to a straight line is the same straight line. Right? If I try to write the tangent line, it's literally the same line, which I know doesn't actually go through one point, but okay. The point I'm trying to make here is that straight lines, we know they're derivatives. We know the derivative of 6x is equal to 6 because that is the slope of any line, any tangent line. We can also use the limit definition. Limit x goes to 0 of f of x plus h minus f of x all over h. F of x plus h is going to be 6 times x plus h. F of x is going to be 6x. And what's going to happen here? Well, we're going to get 6. So 6x plus 6h minus, so let's just write it down, 6x plus 6h minus 6x all over h. The 6x's cancel. This is the limit as h goes to 0 of 6h over h. The h's cancel. So the limit as h goes to 0 of 6. And the limit of a constant is just the constant, right? What's happening to 6 as h goes to 0? Well, 6 is just 6. It's just chilling. So here, for a straight line, the slope is just, or the derivative is just the slope of that straight line, which is 6. It's also true if your line happens to have a slope of 0. Right? What if your line was f of x equal to 3, which looks like, y equal to 3. Well, we know the slope of that line is 0, and the derivative limit definition verifies that. Oops, I need a limit. You always need a limit if you're talking about the limit definition of the derivative. So I'm going to have f of x plus h minus f of x all over h. Okay, I would love an answer from you guys when I ask you this. If my function f of x is equal to 3, no matter what I put in for x, what's f of x plus h? It's 3. So it's not x plus 3. It's actually just 3, right? So let's take a look at the graph here. If this was x and this was x plus h, if I plug in x plus h, what do I get out? Oh, I get out a y value of 3. If I plug in x, what do I get out? Oh, I get a y value of 3. So I'm going to get a limit as h goes to 0 of f of x plus h is 3. F of x is 3 over h. So check this out. Remember, we're finding the limit of the difference quotient. The difference quotient is the slope between any 2 points. For this previous one, the slope between any 2 points was 6. We found that. It was 6. For this one, the slope between any 2 points is 0, right? This point to this point, or this point to that point, right? No matter what 2 points you pick, you've got no rise. So our slope is 0 before we even take the limit. 3 minus 3 is 0. 0 divided by h is still 0. Right? So here we have to remember that h isn't 0 yet until we take the limit. So 0 divided by a non-zero number is 0. This is the limit as h goes to 0 of 0. Limit of a constant is just that constant. So these examples are a little strange. I just want to point them out because there were definitely a couple of homework questions, at least for Win, that ask these kinds of questions. So I have a couple minutes, definitely enough time to talk about being one-to-one algebraically, I think the question was. So how do you show a function is or is not one-to-one algebraically? And I will try and do this the easiest way I know how. Yeah. So show that f of x equal to x squared plus 4 is not one-to-one. If you know it's supposed to be not one-to-one, so how do I say the right words here? To show something is one-to-one, to show something is not one-to-one, you want to show that 2 different x values give you the same y value. Here you can just find them. I know that x squared, negative and positive x values give the same y value. So here I could show by example. Oh look, f of negative 3 is equal to negative 3 squared plus 4, which is 9 plus 4, which is 13. F of 3 is equal to 9 plus 4, which is 13. two different x values gave the same y value. It's not 1 to 1. But maybe we don't actually know what values to look for. In that case, another way of doing it is showing that if f of A is equal to f of B, if we're trying to show it's not 1 to 1, I guess I should say, if you're trying to show it is 1 to 1, if the y values are equal to each other, it had to mean that the x values were equal to each other. So this is typically what we want to show something is 1 to 1. And then if we fail to be able to do this, we've shown it is not 1 to 1. So let me show you how it works here. We're going to assume, I know it's 10:20. If you've got to go, you got to go. Before anyone leaves, just give me 1 sec so I can capture a picture of the attendance. God, there's so many of you. Whoops, not that. So obviously, feel free to go if you've got to go. This will take just a minute to finish up. So we're going to start with assuming the y values are equal to each other. So I'm going to assume f of A, which is a squared plus 4, equals f of B, which is b squared plus 4. And then here, since we know it's supposed to be not 1 to 1, we're going to end up showing that A doesn't have to actually equal B. So subtract 4 from both sides. You get a squared equals b squared. But if a squared equals b squared, that doesn't mean that A has to equal B. Taking the square root of both sides, you get the absolute values equal to each other. So this really means that A is equal to plus or minus B. Really, it's plus or minus A equals plus or minus B. That doesn't mean they're the same. It means they could be opposites of each other. So this would show it's not 1 to 1. We started by assuming f of A equals f of B, and we didn't get that A was equal to B. Let me contrast that with one that is 1 to 1. So here's an easy enough example. Straight lines that aren't vertical aren't horizontal are always 1 to 1. So I want to show f of x equal to 2x plus 3 over 7 is 1 to 1. And the way we do this is to start by assuming, so assume f of A equals f of B. So that means we're going to assume that 2a plus 3 over 7 equals 2b plus 3 over 7. But then we can multiply both sides by 7. So 2a plus 3 has to equal 2b plus 3. Then we can subtract 3 from both sides. 2a equals 2b, and then we can divide both sides by 2. A equals b. So starting with this and ending with this means the function is 1 to 1. Because two different y values being equal to each other ended up meaning that the x values were equal, which actually means the y values were just one y value.